All right, so we are partway through chapter 2. I unplugged my flash drive. All right, let me grab our presentation. We'll be good to go. So kinematics in one dimension, I am in part 1 now, but we'll be ready to do part 2. And let's start right about here. I'm going to start sharing. All right, so we spent some time talking about how to make judgments about velocity graphs from position graphs. I'll just roll back a little bit here. If we can write a position function for our example, like is the case here, this parabola that's got an equation 2t squared, then if we take a first derivative with respect to time, that will yield the velocity graph, or the velocity function, I should say. We can use that to make a velocity graph. So as is the case here, we've got 2 example slopes, 4 meters per second and then 12 meters per second. So even if you forgot the relationship between curvature on a position graph and acceleration, that would be your clue that the velocity is going from slow to fast, or going from big to small. And we can see that those 2 values, so the slopes of the tangent lines at t is equal to 1 and t is equal to 3, match up with the y-intercepts of our velocity graph, where the slope value is just 4 times t. And the units of the displacement function, this is going to yield something in meters. So when we take a derivative with respect to time, we're going to get to meters per second, which is exactly where we want to be. And I just want to point out again here, this S is shorthand for the generic axis, so that if we kind of nail down the behavior or the rules for motion along the S axis, we know that's going to be true for the X axis and the Y axis. All we have to do is swap in either an X or a Y for the problem that we're trying to solve. So we did a few of these thought questions where we were linking motion diagrams to velocity graphs. Then we have a motion diagram. This is another motion diagram to a velocity graph, but here we have a position graph that we were going to turn into a velocity graph. And all we wanted to look for was the sign of the slope here on the position graph, and then whether it was constant or not. So we have a positive slope here. We know that our velocity graph is going to start off with positive values. It levels off so that eventually we get to a section that's got a slope of 0. So we know that this object is going from a positive velocity to 0. C is the only one that makes sense there. So what if we go the other way? If we have some knowledge about a velocity function for an item, we can use that to figure out what the position function has to be. And that's equivalent to starting with a velocity versus time graph and then walking it backward to get a position versus time graph. So instead of calculating a first derivative to go from position to velocity, if we're going to go the opposite direction, we want to compute an integral. So in other words, we can take our velocity versus time graph and figure out the area below that curve and use that to make some judgments about the displacement over that same interval delta t, where the displacement here would just be what I get if I take S final, the final position along our generic axis, and then subtract S initial. So I've got in the limit that delta t approaches 0, we're going to sum up all of these quantities Vs sub k times delta t. So in other words, the integral of Vs dt from t initial to t final added to the initial position on the s-axis will give us the final position on the s-axis. It's like saying, in other words, the final position of the item depends on the initial position, and then how the object changes position over some time interval delta t. So here, the formula at the top is just a repeat from the end of the previous slide. If we have a velocity versus time graph that's not all linear, so if there's some curvature here, then our first step in approximating the area below this curve would be to split this interval into a bunch of bars that all have the same length or the same amount of time, really. So if our entire time interval t initial to t final is this long, if we were to split this up into sub-intervals, all the sub-intervals also have to have the same amount of time. So delta t is going to be the same for all of the bands here in this area. And we can take the value of the velocity that occurs at the midpoint of each one of those sub-intervals and then use that as the height of this little rectangle that we are drawing. So there's a shaded blue one here. The maximum velocity value at the midpoint of t is the midpoint of this little section that has width delta t is about this height. So if we did the same thing for all the other points along the intersection of our green band and the midpoint of our subintervals, then we would end up with an approximation of the area below that curve. We can do one better by allowing the width of each subinterval to approach 0 so that we have a larger number of subintervals, and we're going really from a Riemann sum here to an integral. So let's apply that to a simpler example here. Let's see, make sure my chat window is open. Looks like we're good. Okay, so we've got the velocity graph of an object that's at x is equal to 0 at t is equal to 0. And we want to figure out the position at t is equal to 4 seconds. So the easiest mistake to make here is to not recognize that this is a velocity graph instead of a position graph and treat this as if it says x in meters. You would say, oh, okay, so t is equal to 4. That value is a 0 on the y-axis, so the object is at the origin at t is equal to 4 seconds. And that's incorrect. Since this is velocity versus time, we want to compute the area below the curve. The curve has not just one slope that applies to the entire 4-second interval, but 2 different ones. So we can just split this graph into sections where the slope is equal, or the slope is a consistent value. So for the first 2 seconds, there's 0 slope here. The initial velocity is 4, final velocity is 4. So the area below that curve is just going to be the area of the rectangle that's shaded. It's 2 seconds wide and 4 meters per second tall. So that product is going to be 8 meters. That tells us that the object moves 8 meters from its original position over the first 2 seconds. That kind of lets us eliminate D because we know that the object is still moving between 2 and 4. And next we can just calculate the area of below the curve for this triangle. So 1/2 the base times the height, 1/2 4 meters per second times 2 seconds is going to give us 4 meters. So we add those two together to get the change in position or the displacement between 0 and 4 seconds. That would give us 12. These are all positive because all of my velocity values are on the positive y-axis. If I had any that were below the x-axis, then I would need to treat that area as a negative. So in other words, that would be an object that is moving both forward and backward over the course of the interval that we are evaluating. All right, let's quit sharing here. I'm going to switch to part 2, but while I'm doing that, is there anything from Kinematics and Dimension part 1 that you just need to see or hear one more time? Okay, jump in at any time, either on mic or in the chat. And let's take a look at kinematics in 2 dimensions. You can do some problem solving really for the first time in this half as well. Current slide, okay. All right, I accidentally muted myself for a moment. I just wanted to make sure I wasn't mute and just talking to myself for the whole rest of the morning. So we learned that there's a relationship between a position versus time graph's slope and the velocity of an object over the same interval. Now we're taking that one step further and evaluating the slope of a velocity versus time graph so that we can gain some insight about the acceleration that this object undergoes. And the second half of the thought problem that we just worked through did have a section where the velocity was not constant. So between 2 and 4 seconds, the velocity was decreasing at a consistent rate. We didn't need to know what the slope was in order to figure out what the change in position was over that 2-second interval, but there is a way that we could have solved that same problem using the information that we're talking about here. So in other words, focusing on the rate of change of the velocity as opposed to just computing the integral for that section of the graph. So let's imagine that we've got two cars, a Volkswagen Beetle and then a Porsche, that are both going to go from 0 to 30 meters per second. We want to see which one's going to get there first. So it would be an excellent guess to guess that the Porsche is going to reach this speed in a smaller amount of time than the other one. Because the Porsche, this is a sports car, it's kind of manufactured to be able to accelerate in this fashion, whereas the VW is eventually going to make it to 30 meters per second, but it's going to take a longer amount of time. So these two sections, or these two velocity data sets, both have the same v initial and the same v final, but they do not have the same slope because they don't have the same delta t. So it's not really right to say that one is faster than the other, but we can identify what is larger for the Porsche compared to the Beetle. So now we've got this annotated version of the same graph. We can determine what the slope is for each of these vehicles. And we can start with the Porsche here. So it only takes 6 seconds for this Porsche to go from 0 to 30 meters per second. So that's an acceleration of 5 meters per second for every second, or 5 meters per second squared. That's how we're going to see this more often than not. But meters per second is also a valid way to measure acceleration. Meanwhile, for the VW, that slope value is calculated here in the image. It goes from 0 to 30 in 15 seconds. So instead of a 6 second down here in the denominator, we swap that out with a 15. We end up with 2.0 meters per second for the acceleration of the VW. So in other words, every second that the VW is accelerating in this fashion, it's getting 2 meters per second faster. However, in the same second, the Porsche can get 5 meters, or over the same 1 second interval, the Porsche can get 5 meters per second faster. They both reach the same V final, but it takes a different time to do that. So this is obviously acceleration. We talked about this concept from like a vector standpoint in chapter 1, where if we could make a motion diagram for the two cars, we could determine what our delta V vectors would look like over the 6-second interval for the Porsche, and then over the longer 15-second interval for the Beetle. And then we could draw acceleration vectors that would tell us whether we had an object that was going forward and getting faster, which is the case for both cars here, compared to moving forward at a constant velocity or moving forward and slowing down. We know what those scenarios look like on a motion diagram. However, since we are trying now to relate this concept not only to the slope of a graph, or to a graph, I should say, but also to a derivative, if we have a velocity function for the s direction, v sub s, if we were to take a first derivative of that function, what we would end up with is an acceleration function. So this average acceleration that we see here, this is something that we can define as delta Vs over delta T. This is similar to what we saw in the like the second half of chapter 1. Chapter 1 notes are just in one file, but closer to the end of that, we introduced the concept of average acceleration. And I mentioned that we're pretty quickly going to discard this average subscript and just treat this as the acceleration of the object. But that's kind of associated with us going from this delta V over delta S to the first derivative of the velocity function. So here's that same graph that we saw a few moments ago when we were trying to make some judgments about the change in position or the displacement this object experiences over 4 seconds. Now, if we calculate the slopes of these two segments, we can gain some insight about the acceleration, or in other words, how the velocity is changing as a function of time. So for the first 2 seconds, the velocity is a constant 4 meters per second. So it's no surprise that the acceleration that we end up with is a 0 because the change in velocity is a 0. It doesn't matter how long in terms of time this interval takes to kind of play out. If v initial and v final are the same, the acceleration is going to be 0 over that interval. And now from 2 to 4 seconds, we have a negative slope on this velocity graph. So that's telling us that delta v is going to be a negative value. You're going from fast to slow. And this specifically, since this is a positive 4 meters per second, this means headed or going fast in the positive direction. That could be fast and toward the right, and then slowing to a stop. You're not actually changing direction unless you cross over the x-axis. The slope value here would be negative 2 meters per second squared because every second the velocity gets smaller in magnitude by 2 meters per second. So it's really, really easy to conflate the rules that we laid out for like the meaning of the slope of a position graph with the meaning of the slope of a velocity graph. And we've got a couple of thought questions that kind of ask us to think about both of those scenarios at once instead of just one or the other. So imagine we have a cart that's slowing down while moving away from the origin. So it's moving in the positive direction in this case. What do the position and velocity graphs look like? First, since the velocity is going to be a positive, we can eliminate any one of these graphs where the velocities are negative. So that means B and C are immediately off of the table. We have either A or D. And what we want to keep in mind here is that the derivative of our position graph has got to be equal to, or the velocity graph has got to be the derivative of the position graph. So if we take a look at how the slopes are changing for graphs A and D, we can figure out which one of these is appropriate. So let's look at graph A. We have a flat slope. So this is something that is moving very slowly to begin with, and it ends up moving with a greater speed because the slope gets steeper. So we're seeing something that goes from slow to fast. That's the opposite of what we want to look for. So that means D should be the correct one. We have a slope that starts off steep and it ends up flat. So this is something that goes fast to slow. The slope value begins positive and gets closer and closer to 0, just like the velocity values do. So D is the one that makes sense. Another way to state that is that the derivative of this position graph for set A is not the velocity graph that's matched up with it. All right, let's try another example. So if this cart speeds up from rest while moving toward the origin, what do these position and velocity graphs look like? So we are still on the right side of the origin. So all of our position values should still be positives. That means that B doesn't make sense because B has positions that are negative. It's treating it as if the object is on the left side of the origin instead of the right. It's going from rest to fast. So we would want to look for a position graph that shows evidence of a flat slope in the beginning, a steeper slope at the end. That means D doesn't make sense because it's doing the opposite. So we're down to either A or C. And let's see which of these graphs actually makes sense. We have a position graph that starts off with a 0 value and then becomes or has a slope that is steeper and negative. So that's suggesting that this velocity graph should go from 0 to progressively more negative values. That's how we know that A is not correct and that C is correct. Peek at the chat real quick. It's like we're still okay here. Jump in at any time if you've got questions about anything. I'm going to keep going. So now we've got another thought question. Consider this motion diagram of a car speeding up on a straight road. The sign of the acceleration is either positive, negative, or 0. So we have an object that starts off on the right side of the origin. The earliest point in time is this one here, the particle that's only connected to the tail of a vector, but not a tip. And we have vectors that are getting progressively longer in length. So we know that the object is speeding up. We know that it's moving toward the left. So any scenario where an object speeds up, you know for sure that the acceleration vector and the velocity vector have the same direction. So that means that well, first off, the easiest one that we could eliminate is 0 because these velocity vectors aren't maintaining the same magnitude, but they're increasing. So if the car is speeding up toward the left, that means that the acceleration is also negative. And it's super easy to see negative acceleration and think that that always means slowing down, but it doesn't. If you know the sign of the acceleration, but you don't know the sign of the velocity, you don't have enough information to determine whether the object is getting faster or slower. What you always need to evaluate is how the direction of the velocity vector compares to the direction of the acceleration vector. Because remember, the acceleration vector is based on the delta v vector, so how the velocity is changing. You need to know the original velocity in order to figure out a final velocity. So let me state that another way. If I told you that a car was increasing its speed by 5 miles per hour every second, and then asked you how quickly the car was moving after 10 seconds, you would need to know how quickly it was moving at the beginning of the interval to answer that question. So that kind of tells you why, or it's an example of why, knowing the acceleration with nothing else is not enough to tell you whether the object is speeding up or slowing down. So likewise, negative velocities don't always mean slowing down. Now we are looking at the same scenarios or similar scenarios, but we're trying to evaluate the velocity graphs and the acceleration graphs. So for 18, a cart speeds up while moving toward the origin. It starts off on the right side of the origin. It's moving toward 0, so it's heading toward the left. What did the velocity and acceleration graphs look like? Well, for one, a leftward velocity is going to read as a negative because our arrow is pointing toward the left. That means that A and B are not correct because those velocity values are all positives. So we're down to either C or D. We have a cart that's speeding up. So if we know the direction of the velocity vector, we know the acceleration has got to be the same direction. So negative velocity has got to pair with a negative acceleration in order for this cart to get faster while it's moving backward. D is what would happen if this cart were moving toward the origin, headed left, but slowing down as opposed to speeding up. So our goal is to be able to represent these types of changes in motion in both a graphical sense, but also in a quantitative sense. So we want to build a set of equations or a system of equations that we can use for any scenario where our acceleration value is unchanging. And remember, that can mean that the acceleration is literally 0 and an object is just maintaining the same velocity the whole time, or it can mean that the acceleration is a constant value, so that every second the object is moving, it's either increasing its velocity or decreasing by a fixed amount or a consistent amount. So what we are kind of dipping our toe into is the first of 3 kinematic equations that we can use whenever acceleration is constant. So for example, let's start with this acceleration versus time graph. We are measuring along our generic s-axis again, and we're just concerned with this interval delta t from t initial to t final. So the acceleration value is always the same. It's a positive value. And I should state here that for this data set, the acceleration is a consistent positive value. If we wanted to figure out what delta v is, the change in the velocity that this object undergoes between t initial and t final, we could compute the area below this curve, just as we did when we were trying to go from a velocity function to a position function. So here I have a rectangle. It's a sub s tall. It's delta t wide. So if I multiply those two together, I have a velocity change, delta v. whatever that slope value is that matches up with the y-intercept on our acceleration graph, that will be, or I should say, the y-intercept on our acceleration graph will give us the slope on the velocity graph. So over this same interval delta t, I know that this object goes from having some positive velocity to some more positive velocity. But I should point out that this acceleration graph by itself isn't enough to tell me whether the velocity is positive, the velocity values are positives or negatives.
Sorry,
So in other words,
quick question.
Yeah.
So the area under the acceleration is like, what does that value mean?
It's delta v, so it tells you the change in the velocity of the object over that same interval.
So that is, what does that mean for our velocity graph? Or were you gonna get there? Like,
Yeah, it's the next point.
okay,
So we know if we're just looking at the y-axis of our velocity graph, there's some v initial that has this s subscript so that we are still never mixing horizontal and vertical. We're just looking at one at a time. So for whatever or whichever axis this s is, the object starts off with this velocity v initial, and it ends up with some velocity v final over the same delta t that's described in the acceleration graph.
okay, so from v initial to v final, that number will be the area under the curve, or
Exactly.
the area under the curve of the acceleration graph.
That's exactly true.
Okay, so it's the change in this particular graph, it's like the change in the y value.
For any graph, it's going to be the change in the y value, but the thing that can be different is that there's no reason I couldn't have had a velocity graph where v initial started off negative. And this positive acceleration would mean that negative velocity and positive acceleration would describe something that is slowing to a stop
Down,
as
right.
opposed to speeding up, which is the case here.
Gotcha.
But
Gotcha.
the sign of v initial s could be anything. It could be positive,
Gotcha.
negative, or zero.
Okay. So it could be, it's just a change in this velocity, because the time stays the same, right?
Yes.
So it's a change in velocity. It could be positive or negative.
Right.
Gotcha.
Okay, so now let's look at that velocity graph that's shaded in a little bit. So we don't know about what's going on between t is equal to 0 and whatever our generic t initial is. But we know that over the course of that interval from t initial to t final, there is one rectangle that encompasses the change in position that this object would have if it was not speeding up, but just moving at whatever v initial s is for this interval delta t. And the triangle that's stacked on top of it is something that we can use to figure out how the position changes as a result of the fact that the acceleration is not 0. So in other words, since we know that this object is going from slow to fast, it's going to be traveling a greater number of meters each second than it did the second before. So it might go 1 meter per second for the first second, and then it might cover 3 meters for the next second. And then it might cover 3, maybe 5 meters the next second. So the speed getting larger means that the slope between t initial and t final is going to be non-zero. So if we were to solve for or to calculate the area below each one of these curves, for the dotted line or this dotted rectangle that's marked off, it's as simple as taking v initial in the s direction times whatever delta t is. That's going to give us a distance, or a change in position, I should say, because that's a velocity times a time interval. And for this triangle up here, it's still got the same width. So the base is delta t. But the height now is going to be as times delta t. So 1/2 of as times delta t is going to be just the area of this triangle as opposed to the entire rectangle. That would encompass the space from t initial to v final s to t final. That makes sense? So that's the meaning of this third term here. It comes from the area of this triangle. And the middle term comes from the area of the rectangle. S initial is just how we can control for an object that starts somewhere other than the origin. So if this object starts at 1 meter as opposed to x is equal to 0 meters, all we'd have to do is add that 1 meter on. So S initial will often be 0, but you should never assume that it is always 0. All of these terms are going to give us values in meters or in a distance unit. So we have a distance plus or really a position plus a position plus a position equals a position. This is the first kinematic equation, or sometimes I'll call this the first equation of motion. This one here, S final is S initial plus blah, blah, blah. We're ultimately going to see a set of 3. So now let's look at second slide, the kinematic equations of constant acceleration 2. So we have the same scenario here, the same 2 graphs, the same area below the curve between T initial and T final. But now, instead of just evaluating how the position of the object changes, we're concerned with how the velocity changes. And what we end up with here for the second kinematic equation is literally just our acceleration definition rearranged. So we earlier saw that acceleration was delta V over delta T, where we could expand delta V into a V final minus V initial. So if we solve that expression for V final, what we get is that the final velocity depends on the initial velocity. And then this middle term is the change in velocity that's a result of AS not being 0. Because as soon as AS is 0, then you end up with the statement that V final is equal to V initial, which is true, but it makes this second kinematic equation especially useless whenever you have a 0 acceleration case.
Because if it was no slope, it'd just be a horizontal line.
Yep.
And then at all the time, it would be the same.
Right, and the acceleration's y-intercept would be a 0. And on that same note, to come back to this position expression that we saw previously, this one doesn't become useless when acceleration is equal to 0, because you can still track a change in position for a given constant speed. That would, in other words, V initial and V final are going to be exactly the same value. So if you know the constant speed that this object is moving at, then you can just multiply in a delta T to see how far that object travels in that time period. But this is, sometimes I'll call this like the velocity equation or the second kinematic equation. The two that we, oh, go ahead.
Quick observation for the first equation.
Yes.
It's like basically the same thing in that if it was not moving, the position would just have the one term, right? S initial. But if it was moving in a, just a regular straight line instead of a horizontal line, that's adding the one dimension, so the velocity, so 1 delta T to make it straight, and then if it's got acceleration, that's going to give it a curve, thus the delta T squared. So it's like, right, like x squared makes it, have a curve, in a regular function.
It's exactly that. We don't have all 3 graphs shown here, but the position graph that we could make out of this velocity graph would behave exactly the same way that you said. If acceleration is not equal to 0, then you have something that is going to yield a parabola. So something that is proportional to x squared or delta T squared instead of just delta T. But when the acceleration is equal to 0, you have something linear because it's just whatever your initial constant velocity is times delta T.
Gotcha.
And in the case where both AS and V initial S are 0, it does become useless because S initial is S final. You already knew that the object wasn't moving.
1 equals 1.
Exactly. Okay, so both of those kinematic equations were time dependent. So if we knew how long an object was moving and we knew, let's say, its acceleration and an initial velocity, we could figure out how quickly it would be moving at the end of that time period and where it is at the end of that time period. But it's not a guarantee that you're always going to have information about the length of time that an object is moving. So if you take those first 2 kinematic equations and combine them so that you are eliminating delta T, Eventually what you'll end up with is this statement down here, where this relates the square of the final velocity to the square of the initial velocity plus this term here, a or 2 times a sub s times delta s. And if we just think about what's going on with the units here, velocity squared, that's going to be meters squared over second squared. Then this third term is going to be an acceleration times a change in position. So meters per second squared times an additional meter. So I have meters per meter squared over second squared on both sides of this equation. And for cases where you have information about the distance or the displacement that this object undergoes, then you can get around not knowing what delta t is. But that doesn't mean that you can't use the first two equations to solve a problem like that. It's just a matter of doing two calculations if you were to use equations 1 and 2 together, compared to doing one calculation if you just use 3 by itself.
Sorry, so for the third equation, it's independent of time, right? So it's
Yes.
just displacement.
Yes.
Okay. So the first two had to deal with time, so you can like find rate and what was it? Final position.
Right.
And so this one has no time, so you can only deal with position. You can only deal with the one axis.
Yes. Yeah, that's a way that you can think about it. It's like, it's kind of like combining all three of the possible graphs with the position graph that we don't see here, so that you are eliminating the commonality. You would end up with, or you could make a plot that would show how the velocity changes as a function of position, as opposed to as a function of time.
Gotcha. Okay, thank you.
Okay, sure. And if anybody has any questions or comments, it's always great not to just be talking to myself for a couple of hours. So jump in with anything. So this is our set of 3 equations. The position function for the s-axis, the velocity function for velocity along the s-axis, and then our time-independent one. And as we kind of mentioned a bit earlier, whenever as is equal to 0, these simplify. So one of these equations becomes complete. Well, actually, 2 of them become useless, because when as is equal to 0, you've proven that the square of the final velocity is the same as the square of the initial velocity. That's exactly the same conclusion that you reach in equation 2 right here. But I want to kind of talk a little bit about equation number 1, because it's tempting to think about the version on the left and the version on the right as being 2 different equations, where even though I'm always going to give you the formulas for exams and stuff like that, if you are, or once you get more comfortable with it, these are going to start to stick in your head. So if you are looking for, I suppose, the one that is more appropriate to commit to memory, commit the one on the left to memory, because you can always turn it into the one on the right whenever as is equal to 0. I think we're going to see, yeah, we have some problem solving coming up so that we can see how these work actually in practice. But now we've got 3 graphs stacked together. Up until this point, we've either seen velocity and acceleration together or position and velocity together, but not all at once. We're going to get the chance to collect some data in this week's lab that will let us just set up a motion. So yeah, it'll be the first time we work with our motion detectors, but you will be able to record one event, so a cart moving down a track, and keep track of how its position changes, how its velocity changes, and how its acceleration changes over the same time period. So here on the left, let's start at the bottom. We have a straight line, so no curvature at all. If we were to calculate the slope of this line, we would get the y-intercept of the next graph, which is velocity. And if we calculate the slope of this graph, we get the y-intercept of the next graph, which is acceleration. Now, these are all for cases where a is equal to 0. When a is not equal to 0, instead of a position graph that's linear, we have one that is curved, it's parabolic. And in this case here, it's concave up. So that's telling us that this object starts off moving slowly when the slope is close to 0 ends up moving more quickly when the slope in this case is a more positive value. That
I have a question.
concavity gives us some information about the slope of this velocity graph. So it's concave up here. I would expect a positive slope for the velocity graph. And this slope is going to yield the y-intercept value for the acceleration. And there's a question I was just about to talk over.
Yes, so is it at, like, let's say the acceleration wasn't constant, right? Is it ever useful to figure out the derivative and like, is there, I think it's called what, jerk, right? Is it ever like practically useful to find that and use that?
Not for anything that we're going to be working with, but those higher level derivatives, it goes, so like your first derivative of position is velocity, the second will give you acceleration, the third will give you jerk, and then I think 5, 6, 7 are snap, crackle, pop. This is something that you might run into if you are like if you fly a drone or something like that,
Gotcha.
where the higher ordered derivatives are useful. They're not super useful to us, but they do exist, and that is exactly how you would calculate them.
Sure, sure. Now, is it useful when eating Rice Krispies?
Depends on what you're doing while eating the Rice Krispies. But yeah, those names are not made up. That is how the higher order derivatives were named. I'm not sure who we can attribute that to, but those are the names that match up with them. All right, so we have an example problem here. I'm going to log in to our meeting on my tablet so that we can work it out in real time. But let's just take a look at what the scenario is. A sprinter accelerates at 2.50 meters per second squared until reaching their top speed of 15 meters per second. They then continue to run at top speed. How long does it take them to run the 100-meter dash? So we're going to use that same group of kinematic equations, but we'll have to split this problem into two different sections because the sprinter is not accelerating the entire time. They're accelerating and then maintaining a consistent speed. So let me log in 3:15:77, and then I'll be able to swap. All right, so let's go to OneNote. All right, and this should be us this right here as soon as I seriously, I'm gonna have to sync again. All right then. Maybe I'll just go in and fill in the text later. It seems like I didn't sync before I closed my computer. But that's fine. Okay, so here's the scenario. We have a sprinter accelerating at 2.50 meters per second squared. So we know acceleration, and I'm going to go ahead and throw an x subscript in here. 2.50 meters per second squared. So if we think about how a sprint like this would work, it would make sense for us to say that the initial position is at 0 meters. Imagine it was your job to measure the 100 meters for this, and you had, let's say, a 100-meter stick, just so your life is not miserable. You would want to put the 0 on your 100-meter stick at the location where all the sprinters would start. You know that X final is going to be at the 100-meter mark. And you know that the rules of a race like this is that everybody's going to start from rest. So V initial X is going to be 0 meters per second. And we know that by the time the race is over, the sprinter is still maintaining this 15 meter per second velocity. So V final X for this sprinter is going to be 15 meters per second. What we want to do is ultimately figure out what delta T total is. But this is going to be the combination of the time it takes to go from not moving at all to moving at 15 meters per second, and the time it takes to go from moving at 15 meters per second wherever they are over the course of the 100 meters, and then finishing the race. And I like to make diagrams that look kind of like this for problems like this so that you can split the velocities, or really the sections that all have the same acceleration. So at t is equal to 0, my rectangular sprinter is at 0 meters per second. The race hasn't started yet. They are at the beginning, so x is equal to 0. At some later point in time, the sprinter is going to be moving at 15 meters per second. So V, let's make that a better looking V. V is 15 meters per second. I know they're not at the starting line anymore, but they're also not finished, so we can figure out what that x is. And we know that if the velocity of the sprinter is toward the right, then the acceleration of the sprinter is also going to be that same direction if they're speeding up. So this is A is equal to 2.50 meters per second squared. And then at the end of the race, that happens at some time later than the point when 15 meters per second is reached. They're still maintaining that same velocity, but now the horizontal position is 100 meters. So let's add that as one of our known quantities. So we know that A is not equal, or A is equal to 0 over this interval. And we can split this into delta T1 and delta T2, where adding those together will give us the total time. Okay, so we have enough information to pretty much suss out everything there is to know about this first interval, delta T1. So let's start there. Delta T1, we want to figure out, 1, how long it takes to go from 0 to 15, and then 2, where the sprinter is at this point in time. So we can use a kinematic equation, and there is two kinematic equations that we can use to answer these two questions. So first off, let's start with the time that it takes to go from 0 to 15. So that's meant to be an asterisk. Let's fix that up here. Delta T1 is equal to what? And let me just call this interval 1 so that it is clear that we're looking for two different things. Now, I would suggest using the second kinematic equation for this example, because we know V initial, we know V final, and we know the acceleration. And we care about the time in this example. So there's no reason that we couldn't use the time independent kinematic equation. But since we do care about the time for this question, we're going to end up calculating a delta T anyway. So I'm just going to go straight to equation 2. So VF, I know that this object is, or the sprinter is moving along the x-axis, so I'm going to put x's here. VFX is equal to V initial x plus the acceleration in the x direction times delta T, and this is delta T1. So if I solve for delta T1, delta T1 is going to be equal to V final x minus V initial x over AX. And I know all of those quantities. So let's plug those in. V final X is 15 meters per second. The initial X is 0. And then I have 2.50 meters per second squared for the acceleration. So that ratio is going to tell us how long it takes to reach 15 meters per second. And we end up with 6 here. And let's just take a look at what's going on with the units, because we're still kind of getting our feet wet with this concept. I have meters per second divided by meters per second squared. So that is the same as multiplying by the reciprocal. The meters are gone. 1 of the seconds is gone. So I'm just left with the time. So this is 6 seconds, just as we would expect. Or the unit being seconds is what we expected. So let's go up here and add that information. We just determined that the time is 6 seconds. Now we want to ask ourselves how far away the sprinter is from the starting line when they reach this speed. So let's now choose the position equation. So the final X position, X final, is going to be equal to X initial plus V initial X times delta T1. We're still not concerned with the last part of the race yet. Plus 1/2 AX times delta T1. This term is squared. Let's plug in what we know because we're solving for X final. There's no rearrangement really that we need to do here. So X final is equal to 0 meters. That's the starting position plus the starting speed, 0 meters per second times delta T1. We just determined that's 6 plus 1/2. The acceleration is 2.5 meters per second squared. And then we're going to take 6 seconds and square it. We're going to get that term dropping out, that term's going to drop out. And we just want 0.5 times 2.5 times 6 squared. And this leaves us with 45. And the units here off to the side, we have meters per second squared times seconds quantity squared. So we lose the second squared, we're just left with meters. This is 45 meters. So this tells us that at t is equal to 6, the sprinter is almost halfway through, 45 meters through the race. So we know now that the second interval is just going to encompass the remaining 55 meters. And we know that the acceleration is 0, so the velocity is going to be consistent. We can just solve for delta T2. This interval 2.
It's just 55 divided by 15, right?
That is right, yeah, because we have, I'll call this delta x2 is going to be 100 minus 45 meters, so that's where the 55 comes in. And I'm going to do the long way, even though exactly what you said is exactly right. I'm going to write out X final is equal to X initial plus V initial X times delta T2 this time, plus 1/2 AX delta T2 squared. But the cancellation is going to be different now because I know that AX is equal to 0. And let me write it out like this. X final, the race ends at the 100-meter mark. X initial for this segment is going to be the 45-meter mark. Plus 15 meters per second is V initial X for this portion. I don't know what delta T2 is, but I know that this whole last term is going to give me a 0. So that's going to cancel. And that delta T is just going to be 55 meters over 15 meters per second. 55 over 15 is 3.6 repeating seconds because I have meters divided by meters per second. So we end up with this meters times seconds over meters. Meters cancel. And this is a delta T2. I realize I lost track of that. So now we can fill in this last time. Right here. So I need to add that 3.6 repeating to 6 seconds. So this would be 9.6 repeating seconds. That's when the race ends. So all in all, it takes just a shade under 10 seconds for this 100-meter dash to be completed.
It's a good time.
It is, yeah. It's just over world record, I think. World record is like 9.58 or something like that. So 9.6 is pretty, well, 9.7 I guess is pretty good. Oh,
So
question?
yeah, I got a question for how you, so like, let's say, obviously if this were like a mastering physics problem, we'd have to know how many sig figs, right? But like your notation of 9.6 bar is like infinite sig figs? Is that like, how's that work? Like
Right.
sig figs for the bar?
That's something that I would have to round. So going back to our given values, we have 3 sig figs to work with. So my final answer here should actually be 967. 3 sig figs.
Gotcha.
So that's
Because
exactly what you would want to do to plug in a number if this were like a homework problem.
so
Why isn't
for
it
like the
just one sig fig? I'm just wondering because 100 and wouldn't it only have one sig fig and 100?
It's not clear because you can't see both the PowerPoint and my work at the same time, but the 100 in the 100-meter dash has got a decimal after it, so we can treat all 3 of those figures as being significant. But
Yeah,
if that were missing, you would be correct.
Yeah, I just saw it after I asked the question. Okay, thank you.
so
Okay, you're welcome.
the fact that the final velocity just has 2 sig figs, or does it say 15.0?
It says 15.0.
Gotcha. So everything's got sig figs. So weakest link is 3 sig figs. So he stays in 3
Right.
sig figs. Gotcha.
Right. So really this time would be 6.00. The velocities would be 15.0, but I dropped them. And I really just apply sig figs at the last step.
Sure. Or any pertinent calculations. Is that how that works?
Well, yeah, this question here is just asking us for one thing, which is the time. So it was okay that I pretty much ignored it until the last step. But if, let's say we didn't know what the velocity was at, I guess t is equal to 6, but we knew that the sprinter maintained it the whole time, then we would need to report that speed of 15 meters per second as 15.0.
Gotcha.
Because we'd be starting off with 2 quantities that are 3 sig figs apiece.
And so I guess my question is for like practice of maintaining accuracy or precision or whichever one it is, do we want to keep at least 3 sig figs throughout our calculations if we're to have like any weird decimals? Or do we want
You
to
mean
keep
like
things?
the intermediate calculations?
Yeah.
It would be a good idea to keep as many as you can. So if you are using like a graphing calculator, anything that'll let you scroll up, it's always best to just keep your unrounded values and then round at the very end.
Sure, gotcha. Understood.
Oh, and there's a chat question. Will we be using kinematic equation 1 the most compared to the other 2? Not necessarily. For this problem, we did need to use equation 1 2 different times, but we're going to see coming up later today, actually. So short answer, no, it's not guaranteed to show up more often than the other, but it's not uncommon for us to use that one. It depends on the specifics of each individual question.
Real quick,
Sure.
can you zoom out and get the whole work through? I want to take that for my notes.
That is gonna, I'm gonna upload that. Let me see if I can.
Can't zoom out enough.
Yeah, it doesn't, maybe I've spread it out too much so that it won't go into one page, but I'll
Gotcha.
fix that up so that the PDF will just put it into one page.
Sure. Thank you.
You're welcome. And now that I'm saying that out loud, are the notes from last week on Canvas, or did I export those and then just not upload them in an unhelpful fashion? I think I might have. Yeah, so I owe you, okay, I owe you a PDF from last week's notes as well. So you'll get 2 of them after today's class. Sorry, I didn't notice that before. But if that does come up, feel free to like drop me a line on Canvas if you're looking for the version that we actually work out in class. All right, so I'm gonna leave one of these for bandwidth purposes and then go back to our notes here. Okay, so we determined it takes about 9.67 seconds for this particular sprinter to complete the 100-meter dash. Now, that was a nice, simple, kind of clean problem involving horizontal motion only. So, I mean, if you were the sprinter, you would probably complain if the 100 meters were also uphill or downhill. You know, you would want that type of race to just be a single dimension with no increase in vertical position. But there are scenarios that we're going to be capable of talking about a little bit later on in this unit where objects are going to be moving horizontally and vertically at the same time. Before we get to that point there, we can take a look at objects that are only moving vertically, so no horizontal motion at all, because there is a shared or like a common acceleration that we'll be able to apply to objects that are only moving under the influence of gravitational forces. And this is the concept of free fall acceleration that's kind of highlighted on this slide here. So this image that's on the right-hand side is almost like a motion diagram for 2 different items being dropped in a vacuum. And that is an important note here. Because if I asked you to find like maybe an apple and a sheet of paper and to record yourself dropping both of them from the same height, wherever you are right now, what you would see is not as clean as this motion diagram, or I should say the motion diagram that you would generate from your video would not look as idealized as this one here. And that has to do with the fact that the apple and the feather, or the apple and the sheet of paper, do not respond equally to air resistance. So it's not hard at all to imagine how the feather would drop if you were dropping it in your own room, or how a sheet of paper would. It would probably kind of dance around. It would eventually get to the ground, but it would not move in a trajectory that is as linear as the apples would be. That's not to say that the apple doesn't experience air resistance, because it absolutely does, but it is shaped differently than the feather, and its density is a bit larger than the feathers would be. So that's another way of saying that the apple is more aerodynamic than the feather is, or than the sheet of paper would be. However, in both cases, the reason why the apple hits the ground eventually, or the feather hits the ground eventually, it's just something that we can tie back to an interaction between the planet and the thing that's being dropped. So it might be tempting to think that if you were to put, let's say, the feather on a balance and you measured its mass, you would end up with a mass that's going to be a lot smaller than what you would get for the apple, unless the apple were microscopic and the feather were huge. There'd be a big difference in the mass, is the point there. And the big mass difference would lead to a big weight difference. And it's tempting to say that the apple hits the ground first because Earth is causing it to accelerate at a different rate. than the feather, but the acceleration rates are going to be the same for the feather, the apple. It would be the same for a bowling ball. It would be the same for a person, let's say a skydiver who hasn't opened their chute yet. Items that are moving only under the influence of gravitation and two that are on or near Earth's surface will all accelerate at about this rate here, 9.80 meters per second squared, vertically downward. And this acceleration is a vector because there's no scenario where I would let go of the apple and it would fly toward the ceiling. This free fall acceleration vector is always directed toward the center of the planet. So we're treating that as vertically downward for right now. So you can think of that as toward the floor. But ultimately, we're going to have to take into account that the Earth is not flat, but is spherical. So we're going to have to refine our definition of down a little bit. This is something that you probably did without thinking whenever you learned that Earth was a sphere. So that, let's say, down wouldn't, it would initially appear to be a different direction for someone in the northern hemisphere compared to, let's say, the southern hemisphere or someone at the equator. Those arrows would all point in directions that are not exactly the same. But when you look at a radial coordinate system, downward means toward the center of the planet for all of us. So like I mentioned, we're going to amend this a little bit later on, like in Unit 2, when we actually take the curvature of the planet into account for the first time. So just think about this as toward the floor right now. So you can measure experimentally the acceleration for an object or any pair of objects. And probably what you would want to do in a lab scenario is just take like one object and drop it from different heights and just time how long it takes to hit the ground. You could put that together and come up with an acceleration value for wherever you're located. And I say wherever you're located because this value does change slightly with altitude and like with position on Earth's surface. There are, well, I guess the short story is that Earth's interior is not necessarily uniform. So in other words, we might have like areas of the crust, let's say, near Illyria, let's say, that are a little bit denser than areas of the crust that you might find anywhere else on Earth's surface. So those small changes combined with altitude can cause free fall acceleration on Earth's surface to be a little bit different. I tried to calculate this once for free fall acceleration in LS 112, the room where we meet, and it was like just shy, it was like 9.79 something that would round up to 9.80. So this is something that we can just treat as a constant. So let's imagine that we have a motion diagram for one of the objects that we're dropping from some height. And we are assuming that air resistance is not impacting this object's motion in a significant sense. That's another way of saying that we are imagining that we can conduct this experiment in a vacuum. We'll worry about air resistance in Unit 2. So what we would expect is that this object would start to move down and it would get faster the longer it is moving through the air. So the acceleration vectors that are acting on this object would actually have the same magnitude at all points, or really all midpoints here, because the acceleration vector is something that we can determine based on the delta v vector. So we need two velocity vectors to make each individual delta v. So I've got three velocity vectors that ultimately yielded two accelerations. What I would find is that the velocity versus time graph that I could generate for any object that's moving on or near Earth's surface in a vacuum would have the same slope. And it would be negative because, like I mentioned before, there's no scenario where I drop an object and it starts to move away from the floor as opposed to toward it. So every second that this object is moving, it's getting faster by 9.8 meters per second, but the direction is down the entire time. And we'll be able to talk about what happens when you throw an object up and let it come back down. But for now, we're just talking about motion in one direction. This acceleration vector, A free fall, is going to be coincident with the y-axis. So A sub y and A free fall are the same thing in this context. And we can also express this as negative g, where g is the magnitude of this free fall acceleration vector. Negative is just an acknowledgement of the fact that we made a decision that negative values are going to be down, positive values are up. There's really no reason that you couldn't do the opposite and say that negative values are up and positive values are down. You would end up with a free fall acceleration vector now that doesn't have, or I should say, a free fall acceleration magnitude that wouldn't have this negative sign if you said positive values were down. I'm going to stick with negative values down the whole time. So a sub y pointing toward the floor, having magnitude 9.80 meters per second squared, we can kind of express that as negative lowercase g. And I mentioned that g is equal to 9.80 meters per second on or near the surface of the planet. The further you get from the surface of the planet, the weaker this gets. The direction never changes. It's still pointing toward the center of the planet, but the value would get smaller and smaller. So I should mention that this G value is not going to be the same everywhere in the universe. If you traveled to the moon and conducted exactly the same experiment, you would still see that this object speeds up, but it would not speed up at the same rate. So you would get a graph for velocity versus time that's all negative values, but the slope would be slightly different. G is something that we can predict for other locations, provided we know the radius of the planet or moon that we're talking about and the mass of the planet or moon that we're talking about. So this is an allusion to the fact that we're going to develop another way to confirm what lowercase g is once we get into the second unit. But we're assuming now that we just determine this value by taking an object, dropping it from different heights, and determining how long it takes to reach the ground.
I have a question.
Yeah.
So as you get further and further away from the planet, G gets smaller and smaller, right?
Mm-hmm.
So in like a practical sense, it can get smaller and smaller to the point where it's like infinitesimal, right?
Mm-hmm.
So like, is there any calculations which you would need to take into effect the possibility of other heavenly bodies like acting on an object? Because I know like the moon like causes the tides, right? If you were having a motion problem at high tide where maybe the moon was acting on you, would that affect the speed of gravity?
The short answer is yes, but the moon is the closest thing to us, but it's still so distant that the impact would be something that's kind of difficult to measure. But what you mentioned about this value effectively becoming zero as you get further away is true. It's never exactly zero, technically, but it can be so small that an object that, let's say, you could drop into orbit somewhere near, like somewhere in between our planet and Mars, there is a point where that object would not be, it'd be less likely to move toward Earth, more likely to move toward Mars. It's like a balance between all of the other, because everything in the universe exerts a gravitational force on everything else. But the actual motion that you would be able to observe depends on like how all of those forces combine. I'm saying that in a clunky way. So like each one of us is exerting a gravitational force on one another, but we don't feel each other like dragging one another closer to or farther away from us because we're so close to Earth that Earth's influence like just really, really, really outnumbers all those other small gravitational forces, but they're technically not zero. So they're there, but they become negligible.
Sure, like so the gravity from Alpha Centauri is technically affecting me right now, or the gravity from Jupiter is technically affecting me right now, but it's so infinitesimal that it's in a practical, physical college physics sense, it's not worth including in our calculations.
That, and it's also not enough to overcome inertia. So to get you to go from not moving to moving.
Gotcha.
So
Okay.
it's there, it's just teeny, teeny, tiny. and there is a question about does G change slightly if on Earth if the moon is overhead? Yeah, it would technically. It would get a little bit weaker if the moon was directly overhead because now you've got like two competing sources that are both producing gravitational forces. But again, even though the moon is really, really massive, the fact that it is far away means that its impact is something that you wouldn't even notice. Like I mentioned that you can feel like when you've eaten too much for lunch more easily than you can feel the gravitational force that comes from the moon because it weakens as like 1 over r squared when the distance grows.
I've got a question for
Okay.
gravity. Does gravity affect me instantaneously? So like, you know, like, you know how light travels, right?
Mhm.
Does the force from the gravity from Alpha Centauri affect me instantaneously, you know? Or the sun, or, the Earth? Like, does that have travel time, or?
Not really. It's because gravitation is kind of just based on the presence of mass. So as long as that mass is present and your mass is present, there exists a gravitational force that's like essentially instantaneous that acts on you. So if you were, let's see, if we were talking about not gravitation, but acceleration. So this is kind of delving off into like some topics of general relativity. But the short idea is that if you are, or the short answer is that if you are accelerating in exactly the right way, you can cause yourself to feel gravitational forces that are exactly the same as, or you would cause yourself to feel forces that are exactly as large and oriented in the same direction as what we feel on Earth. So this is what's really, if you like read sci-fi or watch sci-fi, if you've ever seen a scenario where people live on like a donut
Right.
shaped space station that spins,
Yeah.
the point of that is that the acceleration would cause everybody inside the space station to feel exactly the same as they feel on Earth. It's not a gravitational force, but it's an acceleration. But if those two things are equivalent, this is called the equivalence principle, that the right type of acceleration feels exactly like gravitation, you wouldn't be able to tell the difference. So if you were accelerating at the right rate, you would feel as if you were on Earth. Now, the point here, you're asking about if there's a lag time. There would be for the acceleration induced, like false gravity, but not for the real thing,
Right, like travel time.
right?
So let's say that I would, be able to instantaneously, you know, convert energy into mass, right? I could take
Okay.
all the energy in this room, all the heat in this room, and convert it into, a big mass of hydrogen or whatever, right?
Okay.
Would the gravity that mass like creates, would that instantly affect everything around it in the universe, or would it have a travel time? Like, would that gravity take time to affect the star 100,000 light years away?
If it's instantaneous, then no.
Right.
It would
Okay.
just be like flipping a switch.
Huh. Interesting. That might be useful.
If you are like interested in these tangents, there are like a couple of books that I can like point you toward that kind of lets you think through thought experiments like that so that you, or like this one, so that you can get a sense for how relativity works by using like simple examples. Because it's not something that you would ever be traveling quickly enough to, well, let me say it this way, unless you were like in an airplane, you can confirm some of the predictions that special and general relativity make. But otherwise, you're never traveling at a speed that is anywhere near close enough to see any of this. But you can kind of think through it in some simple thought expression or thought equations. So yeah, if anybody is interested in that, let me know because I have a couple of books that I like that kind of hinge on the same thing or that talk about the same topic.
Thank you.
Okay, yeah, sure, you're welcome. And now to kind of scale things back down again, we're going to do a free fall example problem here where we're going to imagine that we toss a rock straight up into the air and let it fall down into the depths of the Grand Canyon. So we're right at the rim. We're going to throw something up, and then instead of like moving our hand, or instead of letting it fall back into our hand, we just move our hand back so that it falls 1800 1830 meters to the bottom of the canyon. So what we are going to be able to figure out is how quickly it's moving when it hits the bottom. This is a multi-part problem. So let me start by just switching over. Rejoin here. Okay, so now let me share. Okay, that's great. Let's go back to OneNote. Okay, so new page here. So here is our basic scenario. Let's imagine, let's say this is our cliff. Here's our person. They throw a ball straight up in the air like this. It's going to reach some maximum height, and then I'm going to display that same particle over here to the side so that we know it's going to speed up as it falls. So in other words, it's going to go up while slowing down. It's going to be stationary for a moment, then it's going to move down while speeding up. This is a consequence of the fact that the acceleration vector, the free fall acceleration, is pointing straight down. And like I mentioned, I'm going to say positive values are up, negative values are down, so that this is negative 9.80 meters per second squared. And we knew, let me go back to the question. So we know that the initial speed of this rock is 10 meters per second straight up. So I'm just going to label this 10 meters per second. This is our green velocity here. So it's directed up to start with. It is released from a position of 1.0 meters above the rim of the canyon. So I'm going to draw a position scale over here where this is 0 meters. Positive values go up, negative values go down. Oh, hold on. This should be 1.0 meter, and then 0 is going to be right here at the rim of the canyon. So negative values are down. We are ultimately trying to figure out how quickly the rock is moving when it hits the bottom of the canyon. So let me extend this. This value right here is going to be negative 1,830 meters. Okay, so what we have to figure out here is how long the rock's going to be in the air. That's the first part of this. And we know that the acceleration that the rock is going to experience is going to be consistent the entire time. So Earth isn't going to pull on the rock harder when it's closer to the bottom of the canyon or less when it's further away from it. So here's our first question. How long is the rock in the air? So we can approach this a few different ways. I think that probably the most straightforward one for where we are right now is to figure out how long the rock spends going up and then how long it's going to spend going down. So kind of sub question here, how far up does it move? I'm going to call this interval delta t1. So I know that throwing the rock up in the air is not going to result in the rock moving up forever at a constant speed or speeding up as it gets further away from me. The velocity and the acceleration vectors disagree. So there will be a point where the rock is going to have a vertical velocity of 0. I know that let me just write out the kinematic equation for the y direction. So this is equation number 2. V final y is equal to V initial y plus AY times delta T1, where I'll plug in everything that I know. I know that eventually the rock's going to stop moving up. So somewhere V final y is going to be 0. V initial y, I'll use like a redundant positive here. The initial velocity is positive 10 meters per second. The acceleration is negative 9.80 meters per second squared because my negative values on the y-axis increase downward. So minus 9.80 meters per second squared. And then delta T1 is what I don't know. So we can solve for delta T1. So if I move my 10 meters per second over to the side, this is going to be negative 10 meters per second divided by negative 9.80 meters per second squared. So 10 over 9.8. This is going to give me a little bit over a second. So 1.020 seconds moving up. So if it takes 1.020 seconds to go up, I can figure out what the vertical position is at that time. So next question here. Oh, let me. So actually, you know what? I'll just make this a 2-part question. So how far up does it move? First, we're going to figure out how long it moves. Then we're going to figure out how far it moves. So y final, this is the first kinematic equation, but written for the vertical direction. Y final is y initial plus v initial y times delta t1. We're still talking just about that upward part of the motion. Plus 1/2 ay delta t1 squared. So I know that y initial is not 0 meters, but 1.0 meter. The initial y is positive 10 meters per second. And I've just shown that delta ty is 1.020 seconds. I'm going to add 1/2 ay, which is a negative 9.80 meters per second squared. And then my delta t squared is going to be 1.020 seconds quantity squared. So we're going to end up with 1 meter plus 10.20 meters because the seconds are going to cancel in that term. And for the next one, this is going to be 0.5 times g times 1.020 squared. And let's not mess that up, typing it in.
Do you have the letter G as negative 9.8?
Yes. So minus 5.102 meters. So 1 plus 10.02 minus that one is going to give us like
10.20.
5.9, yeah, 2.
You said 10.02, but it's 10.20. Just wanted to make sure.
1.02 times the 10 meters per second.
No, when you were doing the previous calculation, you said 1.0 plus 10.02, and it's
Oh, it's at 2.0.
10.20.
Gotcha. So 1
Just want to
plus
make sure.
that minus half of this. Trying to keep my unrounded values here. So yeah, this needs to change, and I'm going to redo this one. So 0.5 times 9.8. Erase a bunch of stuff because I do just want to hold on to that unrounded stuff for later. So 0.5 times negative 9.8 times that number squared. This is minus 5.102 meters. So 1 plus 10.20 minus this is more like 6.10 meters. So now I know that the rock goes 6 meters above the 0 point on the coordinate system. So just 5.1 meters above the point where you imagine letting go. But now this gives me a new delta y, or one that I can determine. So I'm just going to put table up here. I'll use orange. So y is equal to 6.102 meters. So if that is y initial, and I know that y final is going to be the bottom of the canyon, the next part of this question, I'll do over here, is how long does the rock spend falling down? So I know that at the highest point in the trajectory, the rock is going to be stationary in the vertical direction. So this answer, or this part of the problem, is just going to assume that you hold the rock at 6.10 meters and then drop it until it hits the bottom of the canyon. So it's going to be the same position equation again. Y final is equal to y initial plus v initial y delta t. Now this is delta t2 plus 1/2 ay delta t2 squared. Y final is going to be the bottom of the canyon, so negative 1,830 meters. Y initial is going to be the highest point, so 6.10 meters. The initial y for this section is going to be 0 because we have learned everything that we care about for the first part of the problem. So from the moment when the rock leaves your hand to the point where it stops moving up. There's a delta T2 here that's ultimately going to cancel out. And I have 1/2 AY, still negative 9.80 meters per second squared, times delta T2 squared. So this middle term is going to drop. And we're solving for delta T2 now. And splitting it up this way lets us get around using the quadratic. We could have used the quadratic from the jump, but I want to kind of show both ways of solving this. So negative 1830 minus, 6.10. This is negative 1836.1 meters. I'm going to worry about sig figs later. I can divide that by negative 1, well, let me leave the negative where it was. So divided by 1/2 times negative 9.80 meters per second squared. Then take a square root of that. That's going to give me delta T2. So let's do that. So divided by negative 4.9. Underneath the radical, we're going to have 374.7. And the meters that are part of the acceleration unit are going to cancel the meters that are in the numerator, and I just have second squared in the top. Note I have a negative in the numerator and the denominator, so my delta T squared is going to be a positive. Take a square root of that. We have 19.358 seconds. And the question that we're trying to answer is how quickly the rock is moving when it hits the bottom of the canyon. So we can use just the second part of that trajectory from the highest point to the bottom of the canyon to calculate the velocity. So now I'm going to move to the second kinematic equation, the same one that we used in the very first step up here. So next to the highlight, VFY is equal to V initial Y plus AY delta T, but I'm going to use delta T2 this time. So VFY is V initial Y plus AY delta T2. VFY is what we're trying to solve for. The initial Y using this method from the highest point down to the bottom of the canyon, that's going to be 0 meters per second plus negative 9.80 meters per second squared times our delta T that we just calculated. So times negative 9.8, we end up with VFY of negative 189.7 meters per second. And we were given the initial velocity and the initial vertical position to 2 sig figs. So this would become negative 190 meters per second for the final velocity. And just for the sake of comparison, we can relate, or we can convert that into miles per hour.
That's cooking.
Sorry?
That's cooking. Negative
It
190
is,
meters
and there's
per second.
another point I want to make here. So this is like negative about 425, so we'll say 430 miles per hour. But we're making a real big assumption here. We're assuming that air resistance does not matter. So this is an idealized result. Assuming air resistance is negligible, or let's just say non-existent. The rock could reach this speed. But we're going to come back to this problem after unit 2 when we talk about drag, because there is a point where the rock is not going to be capable of speeding up anymore, even though it's still moving down. This is conceptually kind of similar to what happens if you imagine like collecting data on a skydiver after their parachute is open. So the parachute's job is just to make the person's surface area really big so that air resistance will slow them down pretty quickly. But once the parachute is completely open, the person is mostly just going to drift downward at a constant velocity. So they're not in, or they're free falling, but not at the same rate as they were before the parachute was open, which is kind of weird. But the parachute's job is just to provide a whole lot of air resistance so that the skydiver can reach the ground at a non-lethal speed.
So when the skydiver's falling, they have a acceleration due to gravity until they reach their final velocity, and then their acceleration slows to 0. Does the acceleration like slope down to 0?
If you were constantly collecting data, yeah, because the parachute doesn't instantaneously go from closed to completely open. So there is a time where you would see a rate of change or a slope where it's not like an it wouldn't be like an asymptote. There would be some curvature.
What about just the free fall of like the skydiver without the parachute? Would it still slope down to 0 acceleration when they reach terminal velocity?
No, because that person or that skydiver in that case is only subject to the gravitation and air resistance is the only things that are acting on them. So, I mean, I guess they would reach some, or that person could reach some maximum or terminal velocity before the parachute's open, but then opening the parachute would trigger a bigger surface area. So it would kind of cause more drag to act on the person. So the velocity would drop down to a smaller magnitude again. But after the parachute's open, it's a different, smaller constant velocity. And before the parachute is open, there is a point in time where the person would have to go from not moving at all to moving at whatever the terminal velocity is. But the terminal velocity before and after would be really different.
Right.
And then there's a chat comment about astronauts forgetting how to handle coffee when they are on Earth compared to in space. So their confidence as they drop the mug and them looking up is the best thing ever. Do you have like a specific video that you are thinking about? Because I'd like to see it if you put it in the either the chat here or
I can show it.
the
I have
discussion
one on
forum.
Reddit once.
All right, yeah, feel free to share it probably through our Canvas page because we're counting down to our last few minutes here. But yeah, that's a thing you would have to remind your body to account for if you were constantly going back and forth between these two environments.
Yeah, I couldn't stop thinking about it when you were like, well, nothing floats upwards. And then I was like, well, I know that I just kept thinking of videos because there was one I saw where this dude dropped it. The interviewer looks down at it and this dude looks up at the ceiling.
Well, that's actually related to what we were talking about earlier, the equivalence principle, because for like false gravitation, that is the result of acceleration, or in the case of like somebody who's used to drinking coffee in orbit, the space station or whatever they're in is essentially in free fall the whole time as it's moving around Earth. So that type of fake gravity or the lack thereof could cause something to move up because your reference frame is legitimately moving in that case. But if it's just like plain old gravitation that is the result of mass distorting space-time, the object wouldn't just fly toward the ceiling. But there is a distinction that does line up with what we were talking about earlier.
Yeah, I was gonna mention it, but I didn't want to cut you off in the middle of it because it's kind of stupid and not really relevant in a way.
I'm here for kind of stupid and not really relevant, and it is relevant to what we were talking about. So I'm glad that you did bring it up. All right, let's see. Okay, so we have a few more slides in this chapter. Let me switch. Oh, I want to finish this.
Hey,
thought
Professor
here.
Hardy,
Yeah,
you mind if I make a quick announcement?
sure.
Yeah, me and Mike Rodriguez, we were lab partners during the lab. We sort of had this idea of like making a Discord server that's involved with this class that's sort of aimed towards having a like a study group, sort of an informal group on the Discord itself due to the class not having any teaching assistance for this class. And I know that one thing that helped me when I took physics before was really enable like to sit down and spend some time studying with my classmates and some stuff like that. So I'm gonna go ahead and link that in the chat if you're interested in joining the Discord server for the for this class for like studying, and we can sort of go from there. So I'm gonna go ahead and link that. Thank you.
Thank you for reminding me about that because I was about to talk right through. There's another point here. I was talking to Professor Van Arsdale, who's another one of our physics faculty members, and he is offering some like tutoring or like if you have questions that you want to ask Mondays, Wednesdays, and Fridays, because I'm not on campus Mondays and Wednesdays. I am on Fridays, but he is like the lab assistant. He has taught this course before. He's really great. It's probably going to be helpful to a lot of you just to hear the same concepts explained by somebody else. Yeah, so I want to give you those hours as well. He's available. I'll put him in the chat too. Monday, Wednesday, Friday from 8 to 9, if any of you are actually on campus that early, or Monday and Friday from 10 to 3. And he's real easy to talk to. He's a great instructor. He is Professor Van Arsdale. And he wanted me to kind of publicize that or to let people know because of the fact that we're operating with no TA now. So I will not take it personally at all. If you just want to hear this same topic described or discussed by somebody else. And let's see, that's kind of, thank you so much for jumping in, because I was about to forget to make time for that. One thing I want to point out, I was kind of making a point here that in reality, if you conducted this experiment, you would measure a final velocity that's smaller in magnitude than 190 meters per second, because eventually the rock would reach a terminal speed that's smaller than this value. So that is something that's kind of related to the distance that something has over which it can speed up, but a rock and the Grand Canyon, so like nearly 2 kilometers, there's more than enough distance for that rock to reach its maximum terminal speed and then just continue downward at a constant velocity. So we'll revisit this idea once we are about halfway through Unit 2. But this actually makes a really good point to pause, because we are getting ready to switch